So in this lesson, we're leaving the world of all those spontaneous reactions. We went through voltaic cells, standard voltaic cells, which are very rigid. They're always spontaneous with both sides of the half reaction. Okay. We could just use our table. We got to really go back to those skills we learned about predicting chemistry in electrolytic cells. Electrolytic cells do not happen on their own. We have to force them to run. So when you build an electrolytic cell, you're going to need a power supply. So in the lab, we're going to use batteries to power these. We're going to force the electrons to move from one side to the other. Okay? If you don't have a power supply, an electrolytic cell will not run. So that's one big difference. The other big difference in an electrolytic cell is they're in one beaker. We don't have these two half cells like we had before. I'm actually going to draw this first, and then I'll talk about and we'll figure out the chemistry. So what's it made out of? A solid gold electrode. I'm going to draw kind of a short beaker. So we only have one container now. We've got our two electrodes. We've got a gold electrode. So gold is AU, so I'm using its chemical symbol. We got a platinum electrode. Which you should, we've seen them before, and they only ever showed up as an inert electrode. Okay, and it's still going to be an inert electrode. Okay. There's a copper 2 iodide solution. Okay. So that's an ionic compound. So we're going to have to consider the copper 2 plus ion kind of separate from the iodide. I didn't write aqueous, but they're both down in my solution. So we've got a solution. We got copper 2 ions. We got iodide ions. We've got two electrodes. We're going to need that external cell like we had in voltaic cells, that wire, but we need a power supply now. We need something that's going to rip the electrons out of one of the electrodes and force them to the other. Voltaic cells is like water flowing downhill. It's spontaneous. This is like water going uphill. It doesn't do it on its own, but if you have a motor, something that can force the water, you can pump it uphill. Okay. So let's predict what's going to happen in this cell. There's no shortcuts. We've got to make a list of all the species we have in solution, find the best OA, find the best RA. So we've got a gold electrode that can react. I'm going to put my states in now, so that's going to be a reducing agent. Elemental metals are always reducing agents. I've got copper 2 plus ions. Metal ions are always OAs. Sometimes they're both. We got iodide. All the ides for the halogens are RAs. We've got an aqueous solution, so we've got water. And then I don't put inert electrodes on my list. Okay? You can, I won't mark it wrong, but I'm not going to write platinum. It's not an OA, it's not an RA. So now let's do that labeling. Gold's a reducing agent, copper's an oxidizing agent, iodide's a reducing agent, water can be both. And then iodide you have to be a little careful with. I always remember iodide shows up in some weird pairings as RAs, but it's iodide with silver, and that's not what we have, so I don't have to worry about it. Okay? But it's easy to miss iodide and silver sometimes. Copper 2 is not both. It's copper 1 that's an OA and an RA. So we have to find our winners. We scan the top. We've got two OAs. And water is below copper 2 plus. So the best oxidizing agent is that half reaction. So I'm going to summarize that right away. It's the best OA. I'm going to grab that reduction potential. So I didn't label it, but that's the reduction potential for that half reaction. We're going to find the best reducing agent. We got water, iodide, and gold. So we're starting at the bottom of the right-hand column. And the first one we hit is iodide going up from the bottom. Gold is worse, and water is a worse reducing agent than iodide. Okay. So you need your table. So we're writing that oxidation, so it's flipped from what's in our table. 2 iodides will make iodine. And that reduction potential is 0.54. So I've predicted the half reactions. Okay. I've drawn the cell. We could go further and net this up. I'm not going to. You've seen me net this up before. Find the lowest common multiple. There's 2 and 2, so it is 2 added up. So our reactants are going to be copper ions and 2 iodide ions. What I do want to write out is the E naught for the cell. And when you take the OA, you subtract the reduction potential of the RA, you get a negative voltage. So we haven't been seeing negative voltages. Okay. That is a sign that this is a non-spontaneous cell. That is why we need the power supply. We have to put in more than 0.2 volts to overcome this barrier, okay, this deficiency in voltage. Okay. So this is what electrolytic cells look like. What comes next is figuring out the properties. Okay. So this class is going to look at them experimentally, and then we'll come back and summarize all those properties after we've done the lab.